Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today in this video, we will discuss the difference between resistance and resistivity. First, we will introduce the resistance, which is actually the collision and which produce heat, and we will cover the topic of resistance in more detail in such a way. Then after that, we will find some mathematical relationship between the factors on which this resistance depends. So that factors are cross-sectional area, the length of the wire, and similarly external temperature and the nature of material. So all these are the external factors on which the resistance and on the other word we can say that the resistivity also depend on these factors indirectly. We will discuss all these things in this video in more detail, and all these things will be interactive simulations, not in traditional way. So this video is very helpful for you, and let's start the video. Before starting simulation, we have to know the interface of the simulation. Here we have setup button, setup and restart button. Here we have go and pause button, and this is all external conditions on which the current and resistance through a circuit depends, such as the nature of the material. This is the temperature, this is the diameter of the material or the wire, and this is the length of the wire. Here in this panel we have the energy sources such as the AC and DC voltage. We will vary that from here. Now this is the circuit for this simulation. In this circuit we have batteries. This is the battery. This is the ammeter attached. It will show us the current in millimeter and milliampere. So this is further connected through this wire to the bulb here. This is again the ammeter, and this is the switch. Here are three parallel resistors in the form of bulbs, and this is the length of the wire. This actually represents the length of the wire. Here by default it is 61 meter. 61 meter long wire is connected to the first what we can say the first resistor. And similarly here this 1.8 mm is actually the diameter of the wire. So the cross-sectional area of the wire is 1.8 mm. We will change this here from this wire diameter. Here it is by default 1.8 mm. Therefore it is it by default show 1.8 mm. If we increase or decrease this, and we will show how the resistance through this wire as a function of the wire diameter. So how it depend upon the diameter and the cross-sectional area by increasing or decreasing that. So here we will discuss about what is the effect of the increasing or decreasing the length of the wire and the resistance. And here it will show us the resistance and percent, and also it is written here as the percent energy lost to surrounding in the form of heat, and we actually call that energy as a resistance. And that's it. So here as I mentioned before, that this is the wire, and here we zoom a small portion of the wire and it will look like this. And inside if we zoom this wire, it will consist large number of atoms, because every object is made up of millions and billions of atoms. It is the matter. The matter is composed of a large number of atoms. So in this case this wire is by default is copper. Therefore these are the copper atoms, and we know that the copper atom have 29 electrons, and the electrons which is present at its outermost shell. So the electron, this is the copper atom, this is the nucleus having positive charge, and there are 29 electrons revolving around this nucleus, and at the last shell, at the last energy in the last shell we have a single electron. So if and it has very large size, so the distance between this positive charge and this last shell electron is very low, because the distance is high and due to which the electrostatic force of attraction is low. So therefore the hold of the nucleus on this outermost electron is less. Therefore this electron may fly away even at room temperature. Therefore we call this as a free electron. So this is the free electron. And we know that this copper metal and this copper wire is consist of millions and billions of the copper atom, and each copper atom contributed free electrons which is present at its outermost shell. So therefore this white color are the free electrons. So this white color all are the free electrons, and here are large number of copper atoms, and therefore we say that inside this copper wire we have the sea of electrons. And this was all about the interface. Now we have to start the simulation. Here I click on this button, which is the go and pause. So this is the go. If I click on this go button here, and in this case the current through the wire is 0, because here this what we can say, this switch is off. Therefore the current is, this wire is 0 milliampere here from the ammeter. And when the current is 0 milliampere, still there is motion of these free electrons, because we can say that these free electrons are not in rest. It will be in motion every time, just like an atom. It revolves around the nucleus any time, and also from in other words, we can say that it can rotate and circulate around this nucleus. So that's comes that I have discussed in the previous video in the electric current. So this explanation is associated with that. So now the current the current through this wire is 0. The net velocity of these free electron is 0. So if I on this, this is the what we can say, if I on this switch, then large number of free electrons will move from one side of the conductor to the other side, and therefore here now inside this conductor there will be large number of free electrons moving from this is the not a conventional current. Therefore its direction from the negative towards the positive. Here this is direction from the negative towards the positive, and in case of conventional current, this direction would be from this side, from this positive terminal of the battery to a negative terminal of the battery. So here what we are doing so here what we are going to focus on is this is the resistance which is offered by this wire. So now by default the resistance of this conductor is 9.93%, and this is the distance, and this is the diameter as I discussed before. So now from where this resistance come? So this resistance in order to explain this in depth, we have to pause this. So here in this case these free electrons are moving from left to right, and during their motion it is possible that this free electron may collide with these positive copper nuclei, copper atom, and also there is possibility that this negative free electron is collide with this other free electron. So as from daily life we know that when two bodies collide with each other, it will produce some unwanted energy, just like when two cars collide with each other during incident, it produce some sound. So that sound in this case when this electron is collide with this electron, and when this electron is collide with this positive atom of the copper, so during their collision there will be, because these are the charged bodies, so during their collision the heat will be produced. So during the collision, here I am going to change the color of the fin. So during the collision of these free electrons, the heat will be produced. So here it result the heat, and this heat is called resistance. So resistance is this, and there are large number of collision inside occur this rod. So therefore the overall and the summation of all these effect in the form of heat will give us the 9.93% heat, and that's why here it is written as 9.3% energy lost to a surrounding in the form of heat. So the heat come from the collision. This I want to label here. So in the form of heat. So this is that type of energy, and this is actually the resistance. It show us the resistance. Now we will focus on how these factors affect this value of resistance. So here, if we change the atoms which form this wire, so it if I convert it into aluminium, so here now the aluminium wire is connected connected between this battery and this resistor. So in this case, if I on this simulation from here and click on this button, now in this case the resistance is increased from 9 point what was that value? That value was 9.3 something, I think it was the value, and now it increased from 9.3% to 15.3%, only by changing the nature of the element which form this wire. So each element have their own resistance. So here if I change it into the silver, then this is 15.3. now if for the silver it become 9.14. so for the silver it become 9.14. this is for the silver. So this is for the silver, and this was for the aluminium, and this was for the copper. So from here we can conclude that the copper, the resistance of the wire is changing with the nature of the atom from which this wire made up of. So it is the so here I can write it as resistance depends upon the nature of the material. First is the depend upon the nature of the material. So here we saw that. Now I am going to rough this, and now we have to change this other knob here. This knob for wire for the temperature, the external temperature to this wire. So if we increase, so by default it is minus 12 degrees centigrade. So for minus 12 degrees centigrade, for minus 12 degrees centigrade temperature, this value is the resistance value is 9.14 ohm. And now if we increase this temperature here and restart this, this now become here for temperature 0 degrees centigrade, this resistance value become 9.33 ohm. And now further change this temperature to plus 26 degrees centigrade. So for plus 26 degrees centigrade, this value become okay, we have to restart here this. Okay, this value become 9.75. So here this value become 9.75. So from this we can conclude that if we increase the temperature from here in this case from -12, then 0 degrees centigrade, then +26, if we increase the temperature, the resistance also increases. So the second thing I am going to write here is this. So the second thing is this. The second factor is the temperature. In this case, resistance is directly proportional to temperature. Now I'm going to rub this and see this resistance by changing the other knob. Now I am taking this constant here. Okay, I am taking this constant here, and now I am going to change the wire diameter, the cross-sectional area of this wire. In other word, we can say that the area of this wire or the diameter of this wire. So here by default, this diameter is actually 1.8 millimeter, and in this case the resistance is 9.22 ohm. Now if I increase this diameter from 1.8 to 3.2, and taking the data here, which is this diameter become now 3.2. so this is 3.2 mm. In this case this become 3.11 ohm, and further increasing this wire diameter to 5 mm, then for 5 mm, sorry, this is 5 mm, the value is what I'm going to start this, then this is the value. So here is the value is 1.3 ohm. So from here we can conclude that if we increase the diameter of the wire, the resistance is decreased. The resistance decreasing from 9 to 1. So here we conclude that if we increase what we can say, this is the third point, if the resistance is inversely proportional to the area or the diameter of the wire. So if the diameter is increased, this resistance is decreased. By increasing the diameter, the resistance is decreased. So this was the third point. And now the last factor on which the resistance depends is this wire length, the length of the wire. So here the length of the wire by default is 61 meter. So this length is 61 meter, and during daytime, so if the length is 61 meter, so here if the length is 61 meter, the resistance in that case is 1.3 ohm. And now if we change this from 61 meter to 105 meter, so here it become 105 meter, and also present here. Now for 105 meter, this resistance become 2.22 ohm. And taking the other wire, so if it become 200 meter, so if it become 200 meter, so for 200 meter, this resistance become 4.14 ohm. Now from here we can conclude that if we increase the length of the wire, the resistance also increasing. So here from 61 to 200 meter, we increase the length of the wire, the resistance also increased from 1.3 to 4.4. so here is the direct relation between the length and the resistance. So the 4 point is the R is directly related to the length. So So here, if we consider this is the equation 1 and this is the equation 2, so from equation 1 and equation 2, so here I am going to combine equation 1 and 2, and so for the combination of equation 1 and 2, we can write that R is directly proportional to, this is actually 1 over A and this is L, so L by A. And instead of this proportionality sign, we are using the constant and equal sign. So here R is equal to, and constant here is the rho, which is the resistivity, and the L come in its own place divided by A. So this is the relation for the resistance, and these are the factors on which this resistance depends. So here this is the relation for the resistance, and here this rho is actually the resistivity, and we will discuss this resistivity with the help of the next simulation. In the previous simulation, we derived this equation and we conclude that R is directly proportional to L and R is inversely proportional to area. Now we will focus on what is this rho, a constant of proportionality in this relation, in this equation. So here, if I consider that same copper rod which we discussed in the previous simulation, and the length of that copper rod is 1 meter. If I select the length, if I consider the length of that copper rod is 1 meter, and this cross-sectional area of the rod, so if I consider this cross-section area of the rod is 1 meter square, then in this case the resistance of this copper rod will call, so the resistance of this copper rod will call the resistivity. Resistivity is actually the standard for resistance. So here, if we if someone asks you to find the resistivity of material, you will take the rod of that material, and the length of that material will be 1 meter, and the cross-sectional area of that material must be 1 meter square. So during that time, you will find the resistivity, resistance of that rod, and the resistance of that specific 1 meter long rod will be the resistivity of that material. So different material have different resistivity. The copper have their own resistivity, and the silver have their own resistivity, and the other material you see in the universe have their own resistivity. Because if you select 1 meter rod from that material, and if you make the 1 meter rod from that material, it will have their own resistance, and so the resistance of that 1 meter rod is called resistivity. So therefore the resistivity of the material also depend upon the nature of the material. So if we select the insulator, if we select nature of material, so the rho depends upon the nature of material. So if I consider the insulator and make the rod from that insulator 1 meter long and 1 meter square, so if I consider the rod for that insulator, which is 1 meter long, and this cross-sectional area is 1 meter square, and this length is 1 meter, then in this case this will have more resistivity. This resistivity is will high because of the resistance. Here this resistivity is directly proportional to resistance. And similarly, if I take the conductor, so if I take this conductor here, in this case let's say the conductor is this copper. So if I take in order to find the resistivity of this copper, we will take 1 meter long copper rod, and this cross-sectional area is 1 meter square. In this case, the resistance will be less inside this copper rod as compared to insulator. Therefore resistance is directly proportional to resistivity, and therefore we can say that inside the conductor the resistivity which is represented by this rho will be less as compared to will be less as compared to this insulator. Now if we take the semiconductor, semiconductor and make the same rod with the same parameters, their resistivity will be between the resistivity of insulator and the conductor. So this is all about the resistivity, and here we can if we take length and area constant, this resistance is directly proportional to this resistivity. So there is a direct relation between the resistance and resistivity, and this simulation also show us that relation. If I change the resistivity here, if I change the resistivity from 0 to 0.5 ohm centimeter, then this resistance will also increase, which is present here. So focus on this symbol and the magnitude and the zooming of this symbol, and also this on this value and on this resistivity. So I am going to start the simulation. So here by changing the value of the resistivity, this resistance is also changing. If we decrease the resistivity here, then this resistance also increases. So here their size will also increase. So here is a direct relation between the resistance and resistivity. Now here in this basic simulation, and which is very easy simulation, here this is the circuit, and I'm going to close this circle by putting nail here. This is the conductor, then the here will be the what we can say the circuit will complete, and the resistance will be less. So if I put instead of this nail a razor here, then what will happen here? So the resistance through this razor is more, because the electron is present in the valence band. It do not do not allow for the conduction band, and therefore the current flow through this nature of material is less, and their resistance is high, and therefore the resistivity is high, and due to which this the current flow through it is zero, and due to which this bulb do not on. So instead of this if I put the coin here to close the circuit, then again this glow off. So here the same explanation. Here the electron are in conduction band, so therefore it allow the flow of charges, and this is the conductor. Their resistivity is less, and therefore it is glow. Now if I put the marker in order to close this, so in order to close the circuit, so here it mark as insulator. So if the insulator is used to connect these two terminals, then no current will pass through it, and therefore their resistivity and resistance is high. And this is the basic and the very basic simulation for the resistance and resistivity. Now we are going to the last simulation, and which is pretty much interesting. So here I am clicking on this advanced button here, and now this is the battery which is connected through this wire to the same what we can say a bulb here, and this is again connected to this battery. Now the battery is connected through this bulb with this what we can say conductor, and now in this button here I am going to change the resistivity of the wire. So if I change the resistivity, the current flow through the conductor will be also changed. So this is also the explanation for the relation of resistance and resistivity. Here at lower resistivity, the resistance is low because resistivity is directly proportional to resistance. If I increase the resistivity, the resistance inside this conductor is also increase. So due to it, this motion, the current is decreased. So if I increase the resistivity further, then this resistance through this conductor is also increased, and due to which the current is decreased. And if I take the resistivity higher enough, then these motion of the free electron and the resistance inside the conductor, the motion of the free electron means the current is decreased and the resistance is very high. So this also show the relation between the resistance and resistivity. So that's it, guys. Thanks for watching.